Hello, everyone. Sorry for the issue. So anyone can hear us now? Yes. Can you hear us? Okay. Okay.
Excellent.
Perfect. I'm going now. I don't know what the issue is. So now I'm going to share my screen. Let me put myself muted. So Emma, can you see my screen right now?
Yes, yes.
And can you check if others can also see in the chat?
Uh, can you guys see? Maybe just write in the chat. Yes, you see a slide with 3 brains and network schematics on it. Yes.
Yeah. Yes. Yes.
I think we're finally there. there, I think.
Okay. So probably we can start from your second slide or first. I don't know.
Yeah, okay. Well, I can just talk really quickly about the first 2 slides. It's recapping material from Bratislav anyway, so we don't need to spend too much time on it.
Sure.
Okay, so should we just go?
Yep.
Yeah. So let's reorient. I was introducing the human connectome. Yeah, you decide really from Toronto. Yes, definitely. I was just introducing the human connectome, which I don't need to do much of because Bratislav has already done such a fabulous job. Over the past 15 years-ish, we've learned an awful lot about the structure of the physical wired structural connectome and the functional connectome in the human brain. Can you, yep, next slide. Someone's asking, can we get full screen? And so what you're seeing on the little schematic, you already saw one just like this. On the left-hand side is how we derive structural networks. So you would create an anatomical parcellation to divide the brain into nodes, and then the edges between these nodes in the structural brain network are physical white matter tracts. So then this is a structural physical network. And on the right-hand side, you're seeing the path to create functional networks. So you would have recording sites, e.g. from fMRI or EEG, which then results in time series data. You can correlate these time series and end up with these functional networks where edges are now co-activations between regions, correlations between activity levels of each region. Next slide. Yeah, this is good. So this is where we tried to, this is where we got to last time. So the human brain time and time again has been shown to not exist in a state of perfect order, like a lattice, like you're seeing on the left, and not in a state of perfect randomness, like you're seeing on the right. It exists in this complex topology in the middle, where we see some order and some randomness. And we see the same patterns time and again, as Bratislav already pointed out to you. And this type of network exists in a space where there's a reasonably high efficiency and a suboptimal cost, but the trade-off is that you get a better efficiency for it. So we know all of this about healthy brain networks, which then allows us to start asking about unhealthy brain networks. Next slide. So for example, many disorders like depression can be thought of as network disorders. So what you're seeing here is a few subnetworks of the brain that have been shown to be associated with functional structure in depression. So for example, elevated connectivity in the affective network and default mode network is associated with rumination and other depressive symptoms. And in other networks, a reduction in connectivity is associated with measures like anhedonia. Next slide, please. And we're now able to start saying, well, if we know what a healthy brain structure looks like, and we're starting to see a structure in disorder and disease, can we make this structure look a bit more like the healthy one as a treatment? And TMS, transcranial magnetic stimulation, is a therapeutic network intervention that's approved for use in Canada and the US. And this is sometimes used to treat treatment-resistant depression in particular. And us from Network Neuroscience, our idea is we can start to use the network structure to really manipulate the signals and guide it to states and structures that are more like the healthy brain. But here's the thing, the way this is used in practice at the moment is a one-size-fits-all approach. There's just one point on the brain where everybody gets zapped, and it's pretty much measured by putting fingers on the back of the head. And we're not the same. So next slide. There's approaching 8 billion of us on the planet with a remarkable array of diversity and differences. Our brains don't look the same any more than our external appearances do. Next slide. In fact, our brains, they each have unique fingerprints. We can identify a person's brain structure. We can identify a person's just identity from looking at scans of their brain when they come to sessions days apart. We have reliable structures in ourselves that are amazingly different to everybody around us. So next slide. But clinical approaches are not taking this into account yet, at least in this circumstance. So this is where we enter network control. Next slide. It's one of the few techniques in network neuroscience that is promising a way to bridge the structure and function of the brain, one of the holy grails here. And this is how I always start the analogy with a car. So what you're looking at is a decomposed car of many pieces. And we know how these pieces all fit together to make one vehicle. And if we want to drive a car, if we want to move it somewhere, we don't need to move all of these pieces individually. We just need to move the steering wheel, the brake, the accelerator, and perhaps the clutch. And the reverse question from network science is, okay, we know how a car is built and this was designed this way, but natural systems, they're not, of course. But given the map, could we find things like the steering wheel, the brake, the accelerator to be able to drive it to states that are desired for us? Next slide. So the underlying principle from all of this is that we're trying to drive a system from some initial state that we find it in to a desired final state. And in the brain, we're often thinking about an initial unhealthy state, such as someone suffering from depression, to a desired final state, which is more healthy, therapeutic for the person. And mathematically, a system is controllable if it can be driven from any such initial state to any desired final state in finite time. Next slide. So in the following, I'm going to adopt open loop control with linear time invariant dynamics. So what you're looking at here is X represents the state vector, so the dynamics of each node. A is our adjacency matrix. This is the structural connectome. This is all the pathways that could exist in the system. And U is an input vector. So this is telling us where external stimuli are applied. So where your TMS pulse goes and what the TMS pulse looks like. And B is saying where it goes. Next slide. And then with this framework, we can start to ask questions about navigating state space and moving the brain states across the energy landscape to desired final states via suitable inputs of TMS signals in suitable locations. Okay, next slide. And this allows us to start asking about personalized network-informed target sites. So remember, all people are doing at the moment is measuring with fingers and zapping at a point on the head, and we can do better. So next slide, please. So what we did in this study was to take some data from the Human Connectome Project. We had 36 healthy individuals. We had DTI, structural data, and resting state fMRI, functional data for each person. And for the atlas, we didn't just adopt a standard one. We created an ad hoc brain parcellation of 226 regions of interest, covering cortical, subcortical, and cerebellar structures, so that we could end up with really highly individualized functional and structural connectomes. So next slide. Thanks. For the cortical regions of interest, we use the Schaefer Atlas of 200 parcels. This distinguishes 7 functional subnetworks that you're looking at: default mode network, frontal parietal, visual, limbic, sensory motor, ventral attention, and dorsal attention network. And we mapped this to individuals' free surfer parcellations using spherical registration to get something highly individualized. And similarly, we applied a similar approach for 14 cerebellar regions and 12 subcortical structures, including thalamus, putamen, and cortex. So the result at the end of this is we have really highly individualized structural connectomes and highly individualized functional time series that are on the same map. So these are just 3 example subjects to show you what the structural connectomes underneath them look like. And the main takeaways from this really are, at a high level, you're seeing the same thing, right? We all have the split into 2 hemispheres, the cerebellum's very separate. We're seeing roughly the same functional networks in the same areas. But when you really look at this and you look at the details, there's a huge amount of variation between each person. In different locations of regions, different strengths of regions. So we're getting, like I said, on a global level, we see the same structures, but on an individual level, there's a lot of variation at the nodal and local level. Okay, next slide. So now we have these highly individualized connectomes, and remember the ultimate goal is going to be to drive to some desired final state. We asked, how could we go from an initial state, which we define using the functional fMRI data. So we look at the time series in the fMRI data, and we choose baseline states from this data. So it's really data driven. And we ask, how do we go from this to a place that we define that is activating particular functional subnetworks? Yeah, thank you. So what you're looking at here is the sensory motor network. Suppose we wanted to activate this, and you're seeing the regions in blue on the brain at the top. What that would look like in practice, as you would apply the TMS pulse somewhere that we simulate. And if you've done this correctly, you'll find that the sensory motor network is then more highly activated than the rest of the brain. So nodes here are bigger when they're more activated and smaller when they're less activated. So our goal is to activate entire subnetworks of the brain. So how are we going to do this? Where would we stimulate? Next slide, please. Well, we compared 3 different scenarios. The first scenario is what we've called traditional stimulation sites. So this is scouring the literature and see what's actually used in clinical practice, what's used so far in the literature. If you wanted to stimulate this subnetwork, this is where people are going to go. This is what they're going to stimulate. So next slide. Scenario 2, we chose a path length based approach because really you should keep things exactly as complicated as they need to be and no more. So let's try something simple. Why would we need the control approach if something more simple worked? So we chose regions that had the shortest path lengths to the subnetworks that we're interested in stimulating. So if we're looking at the sensory motor network, we would select the node that is closest to all of the nodes within the sensory motor network. And next slide. And finally, we chose a third stimulation condition of network control theory driven sites. So this is where we just run the simulations for open loop control, and we select the stimulation node that is able to create the greatest activation in this particular network. Next slide. Yeah, so altogether, you've got these three different scenarios. One that is driven from the literature and you see in clinical practice. Two is a really simple network measure, just how far away is it in terms of path length. And three, we run the network control theory simulations to come out with the nodes that create the greatest activation. Next slide. And to take this one step further, previous work that's out there has highlighted an issue that in order to guide a system to a desired state, the number of nodes stimulated often has to be relatively high, as many as 25% of the network. That's not practical for us. And at the moment, TMS approaches can enable the application of no more than 2 stimulation targets. This is by means of double coil use, also known as cortico-cortical paired associative stimulation. So we systematically looked at pairs of nodes as well, because this would still be experimentally feasible later. Next slide. So in our 3 conditions, we looked at pairs of nodes. So the first one, we picked the nodes that's most commonly used in the literature, the nodes that's most commonly used in the literature, and then the second most commonly used, and stimulating both of them. In the second case, we chose the 2 closest nodes to the subnetwork. And in the third case, we ran simulations for pairs of nodes to come out with the pair that created the greatest stimulation. Next slide. Thank you. And of course, the sanity check for all of this, especially with something like TMS on the brain networks, spatial properties are going to have a huge effect. So we had 2 null models, one of them to control for the topology of the network, the topological null model. This is a weight reshuffling procedure that preserves degree, strength, and weight distributions. The schematic is really oversimplified there with just edge swaps. This doesn't work for strength and weight. It's just to give you the idea. We reshuffled edge weights to preserve all of these distributions. And we also made use of a spatial null model. So in the brain, you see this weight distance relationship, a log distribution that you're seeing in the graph. So we make sure we preserve this distribution to control with the spatial null model. Next slide. Thank you. And all together now, this is giving us this setup, right? So you've got this little toy network. I can't use a laser because I'm not showing the screen. So you've got the little toy network with the user bit on the left. So this is like your brain in the initial state. And there's different nodes that are selected from each of these scenarios. The blue, the traditional, the orange is the path length personalized, and the green is the control theory personalized. So the first one is a one-size-fits-all approach, and the second 2 are personalized to people. We then simulate stimulating these regions and see what happens and see how close they're able to get to the target state. And they all should do an okay job. They wouldn't be being stimulated if there wasn't a reason to be. So we're expecting them all to do a semi-reasonable job, but the question is which does a better job, which gets closer to the target states that we're interested in. Next slide, thank you. So this is the first results for the default mode network. So what you're looking at on the top row is an initial state for an individual of different levels of activation across the brain. And then our target state is to activate the entire default mode network. And what you're seeing in the brains below is the regions that come out from each of these approaches. So the blue ones from the literature, the orange ones from path lengths, and green ones from network control. They're pretty different, right? There's quite a lot of variation between where these are coming out in the brain. There's some consistency in prefrontal cortex, but we're seeing a bunch of variation towards the back of the brain for the more personalized approaches. Okay, next slide. Thank you. All right, so what you're seeing let's focus on the left first, where you've got panel A. So again, the shaded gray area, this is what we're trying to activate. This is the default mode network where we want to activate the whole network. And underneath it is the most common regions across the whole cohort. So that the larger orange one, I mean, this is the same for everyone anyway. This is the traditional stimulation sites, but this is what we use for everyone. And then the larger green one is the most common area across individuals from the control theory based approach. But you're seeing a bunch of variation in the smaller dots of what come out for different individuals. And then on panel B, you're seeing propagation as you stimulate these nodes and then see how the signal progresses through the brain. So the big things to take away from this is all three approaches show an early preferential engagement of nodes belonging to the network of interest, so belonging to the default mode network, but only the one that's just optimizing for network control is able to engage the most nodes of the default mode network. In particular via the early recruitment of temporal nodes, which are really poorly reached by other approaches. And the dots in these images are larger if they reach there earlier. You don't need to go back, this is good. So how do we look at the efficacy here? If you look at the orange and red ones, these are all from the literature. So the yellow one and the orange one are the left precuneus and the right prefrontal cortex. And they perform reasonably. So these are like the amount of nodes in the default mode network that are coming out to be highly activated. But then if you move to the right and look at the blue ones, this is now path length. This is now performing marginally better than what's in the literature. And then move to the right again to see the green ones. And this is just from choosing the best according to network control theory. And these are massively outperforming all of the approaches to stimulate default mode network. Finally, in gray, you're seeing topological null model and spatial null model. They're both performing badly, which is showing that topology in space is important. And importantly, the spatial null model performs a bit better, which is showing that there are significant spatial effects in this. Okay, next slide. So then we checked for specificity. So we know that we're activating a bunch of the default mode network, but are we only activating the default mode network? Or are we just activating all parts of the brain? So we checked for nodes across other networks to see how much we're activating all of them. And we saw a great specificity. So we're seeing 88% of the nodes that are most highly activated are within the default mode network. And the remaining percentages are in frontal parietal and limbic. Okay, I just saw a question. The state is assessed through fMRI or with which modality? Yes, it's with fMRI. Okay, next slide. So just a comment on individual variability. This is one particular subject, and in yellow is highlighted the node that comes out as predicted by network control theory to be the optimal one to stimulate to activate the default mode network, and highlighting the fibers that it predominantly travels along to do this. Next slide. And then when you compare these to other subjects, we're getting really wildly different results. So with the same result of trying to activate the default mode network, different individuals' brains are coming out with very different predictions for where we should be stimulating to achieve this goal and the fibers that it is utilizing to do so. Next slide. This is just all on one. So you're seeing everything together. So these brains at the bottom, you're seeing all of the possible sites that were predicted across the cohort, and all of the fibers that are associated with performing this again. And the clean brains with the yellow dots at the top show everything in a neat spread without the mess of the fibers. And next slide. So just to root us back in reality of one reason that we might really care about this, there's a recent paper out showing that in schizophrenia, if people with schizophrenia perform mindfulness meditation such that they suppress activity in their default mode network. The setup you're looking at, without getting too into the details, is they're getting feedback all the time of whether they have high or low activity in their default mode network. When they're able to suppress this through mindfulness meditation, they're able to improve symptoms of auditory and visual hallucinations for several weeks after scanning, which is amazing. So if we're able to suppress an entire default mode network, this is the kind of thing that we'd be able to do with that. Okay, next slide. And I'm aware we're running out of time. So that was just for default mode network as a working example, but we did the same calculation for all of the 7 resting state networks from this parcellation, and here are the rest of them. And the story is pretty consistent across all of them, right? The sites from the literature, they're always performing the worst, except for visual network. Visual, they do a lot better. But otherwise, they were performing the worst out of these methods. Even a simple path-based approach seems to elevate how much of the subnetworks that we're able to activate compared to what's found in the literature. And network control theory, of course, is always performing the best. And similar results for spatial and topological null models. Okay, next slide. So we looked at the specificity for all resting state networks as well. And overall, it was very high, very good, especially for the ones we're looking at. So default mode was 88, frontal parietal 84%, visual was the best with 98% specificity, and limbic 97. Next slide. I think it's struggling to load these images. Hopefully you can see them well enough. So then there's sensory motor network, ventral attention and dorsal attention. They did not perform as well. Sorry, I think that was my email. Yeah, they did not perform as well. Sensory motor was only 23% specificity, so this was surprising. These 3 subnetworks just did not have the same level of specificity as the previous 4. Next slide. So we computed a Pearson's correlation matrix of the internetwork structural correlations between these 7 functional networks. And we found high correlational values for white matter bundles between sensory motor, ventral attention, and dorsal attention network, which probably explains why we're not getting this level of specificity here, because they're all very tightly connected with each other. Next slide. Yeah, thank you. So, of course, the motivation of all of this is to treat various disorders and diseases that would benefit from this kind of approach of stimulating entire subnetworks. So one of these approaches is depression. We created a meta-analytic activation map by searching with neurosynths through the literature of regions commonly associated with depression. So we're seeing subgenual cortex, and we created these activation maps to define new target states. So before, our target states were these functional subnetworks, default mode, etc. But now we changed that to be particular activation maps associated with depression. Next slide. And more of the same. We saw the same level of success that regions that are in the literature so far for targeting these regions to treat depression, they perform the worst in terms of actually activating the regions that we're hoping to activate. And network control theory vastly outperforms. And again, even a simple path length approach outperforms the literature. Next slide. And one more, the same story. The same approach with depression. We looked at regions associated with cognitive control. And yeah, we found the same results of the network control approach, vastly outperforming the literature and path length based approaches. Yeah, next slide. So just in summary, our simulations predict that the network control framework can provide a way to systematically assess the efficacy of stimulating different target sites to activate whole subnetworks. So not just particular nodes, but entire subnetworks. And we predict that network control can identify target sites that greatly perform other methods, and even simple path length approaches will perform better than the current clinical standard. The individual network itself is crucial to take into account. Our brains are really different, and physical proximity alone is not enough, and neither is a group average. We hypothesize that the trajectories induced by network control predictions are more direct and require less control energy. And ultimately, this will lead to potential applications for disorders, including depression, and for improving cognitive function. Next slide. So this is from a paper that's under review. There's the full list of authors at the bottom. And I wanted to really big up Ariana. She's an incredibly talented student who's performed all of these analyses. So really real credit to her, and been working closely with Emiliano and the wider team at the bottom there. So thank you to all of these people. None of it could be done without every single person on the author list at the bottom. And last slide to just finish off. Thank you, and thank you for your patience with all the mess of getting this started. I can answer any questions, or are we doing those later?
Wonderful. Thanks so much. Next level. I think we will open up to questions that are all in the box. And then we will maybe move on to the next talk. I've been advised by Scott to do that. So I don't know, Emma, if you can see the questions in the chat box, or I can read them out. And then I'll let you read through them.
Well, I mean, I see the chat box, but no questions yet. Is that right?
So this is a question from John saying, I don't think I properly understood the selection of stimulation sites based on network control theory. If you select sites using direct stimulation of individual sites to determine those that yield the greatest target region activation, aren't those sites guaranteed to give the most, to activate the target regions the most?
Yeah, right. So we've got the three approaches of taking from the literature, taking path lengths, and then running the open loop control simulations to get what is the highest. The open loop control is going to perform the best, but we would expect that the others perform pretty good too. And the surprise is that they don't. That things in the literature are coming out very differently when we run these linear dynamic simulations. And yeah, the surprise is they're really not coming up to scratch against these methods.
Great. And then we have one final question from Matteo. Hi, Matteo. The overlay between the reach states and the underlying bundles looks amazing. Are there any articles that you can suggest showing this kind of approach, such as stimulating one end of the arcuate fasciculus and getting the target site at the other end, for instance?
Oh, I can't. I'm sorry. Yeah, I don't know of any that are specifically stimulating particular bundles to try and stimulate other regions at the end there. I'm not aware of any of these. There's some really new approaches to try and reach target states. And yeah, I don't think anything's systematically gone through like that. At the moment, if anything on the network front, people just go, there's the strongest connection. I'm just going to stimulate the one with the strongest connection to try and hit my target state. And that's about where we are at the moment, rather than systematically doing everything.
Fantastic. So thank you so much, Emma. Thank you for a wonderful talk and for really giving it with all the technical issues. We really appreciate it. Thank you all for attending, and please, we can mosey on over to the next talk by Amy Kuczewski.
Thank you.
Thank you. Thanks, Emma. Thank you.